Hello, my name is Nathan Kirk, and today I'd like to talk about the topic, how fast does current travel? Let's begin. So first of all, I'd like to pose a question. Who would win a race between a lowly sloth and an electron? So the answer seems fairly obvious. We all know that sloths are very, very slow, and we know electricity is extremely, extremely fast. We assume nearing the speed of light or something close to it. So we would always assume that the electron would easily beat a slow sloth. But let us find out. So let's assume that they're running on a track, like any good running race, and that this circuit is our track. Here at the bottom of the circuit, we have the on and off switch. We also have a battery here on the right, and on the left, we have the lamp. So let's assume that the sloth and the electron are starting this race, and they start down here at the bottom near the on and off switch. And the first one to get around the circuit to the lamp is the winner. Okay, so let us begin this race. Make your predictions. If I had an iClicker right now, I'd let you make a hypothesis, take a guess. Who's going to win, sloth or electron? Ready, set, go. And the winner is, drum roll please, the winner is this sloth. The sloth pulls off the amazing upset and beats the electron in this race. The sloth, dressed up very nicely here, somehow manages to beat the odds-on favorite, the electron. So how is this possible? How does the sloth beat the electron? Let's find out. So the first question is, why does the sloth win? And the second question is, doesn't electricity move at the speed of light? So it would almost beat anything, sloths included. Well, to answer this question, let's first we have to define what current is. So the electric current through a region of space, such as this wire in a circuit system, is equal to the amount of charge that passes by a given area per unit time. So the best way to say it is the flow of charge. And we know, well, because of Ben Franklin, it goes from positive to negative. So let's move on. Here's a diagram of current. As we can see, it's the amount of charge that flows through a given area over a certain amount of time. So that's the equation for current. I, meaning current, Q is the charge, and T is time in seconds. Q is measured in coulombs. Charge is measured in coulombs. Current is measured usually in amps, and time is measured in seconds. So let's do a little practice problem here for using this current equation. It's a very simple problem. So how much charge passes a certain point in 10 seconds if the current is 10 amps? So first of all, we can write down the information that we know. So we know the current equation is I equals charge over time. I equals Q over T. We know the time is 10 seconds, and we know the current measured in amps is 10 amps. So by rearranging this equation, we can see that we can put charge equals time times current. And so substituting those values, we get charge Q is equal to 10 seconds times 10 amps. And so we know that the charge comes out to be 100 coulombs. It's pretty simple, and using this equation, we can find out these three separate variables. So now the question is, how fast? How fast is this current traveling? So we know that electric fields typically propagate through conductors at around 10 to the 8th meters per second, or 1.0 times 10 to the 8th meters per second, which is 33% of the speed of light, or a third of the speed of light. So still incredibly, incredibly fast. Would beat almost anything in a race, I presume. So, fun little fact here, if you flip a light switch here on Earth that connects to a light bulb on the moon, then the bulb will light up about 1 second later, which is kind of cool. I thought was really interesting. Individual conduction electrons in typical metals move at about 10 to the 6th meters per second, which is 1% of the speed of light. Moving on. So this brings us to drift velocity. And drift velocity is the average velocity of the free charges, which is extremely, extremely, extremely small, which means it's very, very, very slow. So how can we compensate for this? That drift velocity is so slow, and electric current is extremely, extremely fast. So we can see that drift velocity tells us that electrons move at about 0.0007 meters per second, which is equal to 0.000144 miles per hour. So this gives us the answer to why the sloth beats a free charge electron in a race. Because the maximum speed of a sloth, extremely, extremely slow, is 0.003 miles per hour. But this is still faster than a free charge electron. So this is why the sloth wins the race. So it begs the question, like I said before, if the electron is so slow, how does electric current move so fast? It's a really good question. Let's find out. Here we have an example of a line of marbles, and we can see that there's a wooden block at the end of these marbles as well, and someone is, with their finger here on the right, is pushing the one marble into the next marble, which domino effect hits the next marble until eventually we knock over the wooden plank at the very end. So we see here a series of collisions between the marbles, and this is a perfect example of how free charge electrons move in electric current. So we can imagine that each of these marbles is a free charge electron. So we know that the electrons, because of drift velocity, are moving very, very slowly. However, because there are so many of them and so many series of collisions that we can see, one hits another, which hits another, which hits another, the electric current, this represents electric current, moves very quickly, and with just one movement of this marble on the right, all of a sudden the wooden plank at the very end, because of those collisions, is knocked over and we have electric current. So this is pretty cool. So the electron's slow, electric current very fast because of these collisions between electrons. So the basic idea is that free charges push on other charges, which push on other charges, which push on other charges forever and ever and ever, meaning that this is how electric current flows. This is how it flows so fast, so quickly, despite the fact that the actual electron itself, because of drift velocity, is moving very, very slowly. Thank you for watching. My name is Nathan Kirk. See you later.